a weighed sample of iron, okay, is added to bromine, okay, and reacts completely, aka there should be no iron left, theoretically. The reaction produces a single product, okay, one product that can be isolated and weighed. And the experiment was repeated a number of times with different masses, but with the same mass of bromine. See graph below. So exactly, we have effectively this. This is our graph that we're working with, okay? And we can see here that this will be 11 based on the peak, and this right here was 2. And yeah, that is really all the information you kind of need right now. We have mass of iron and then the mass of the product. So with this being said, let's start with question A. What mass of Br2 is used when reaction consumes 2.0 grams of Fe? So for this is going to take multiple steps, because the first thing we have to do is find out the in a sense the formula that we're even working with here, because as we know with iron, because it's a transition metal, it can have different types of like iron 2 versus iron 3, but we can see here, right, the mass of iron is going to be 2 grams of the 11. That means bromine had 9 grams of bromine had to be used. No, sorry, actually no, it still makes sense. 9 grams of bromine has to be in that massive product if it reacts completely, because it used up all the mass of iron. So that means the only mass left has to be bromine, which is 9 grams of bromine, okay? And now what is a mole ratio of bromine to iron in this reaction? So we say 9 grams of Br2, okay? And that's important to note, because the fact that when we're doing the mole ratio, we're going to have to use Br2 as the molar mass and not just bromine by itself. So mole ratio of Fe to Br2 in reaction. So we have a grams ratio of 2 per 9, because it looks like 2 mass of iron was used per 9 mass of bromine of Br2 to produce the mass of the product. So with that being said, we have now, just as a double check in terms of the moles, we would need to convert the iron first from the mass to the moles. So iron by itself has a molar mass, a molar mass of 55.845 grams per mole. And we start out with 2 grams, okay? To get rid of the grams, we need to divide. So that's 1 mole is equal to 55.845 grams. And so we realized that what we're dealing with for the grams was actually just 0.0358 moles of iron. Now bromine, as we said, we have 79.904, but because we want to do the molar mass of bromine gas or liquid, it's still Br2, so we have to multiply that atomic mass units by 2. So we have 9 grams, okay, divided by 1 mole of Br2 is 159, because 79.904 times 2, 159.808 grams. So 9 divided by that, we have 0.0563 moles of Br2. So if we're to just divide these together, okay, as in to get the ratio, we will divide the iron by the lowest number, so that's 0.0358 to get ratio of 1 so far, and it's going to be 1, 2, as in 0.0358. This ratio here is going to be 1 to about 1.57. So a little bit unclean, but if we were to, I guess, kind of do an estimate, we would have almost, okay, a 1 to 1/2 or a 2 to 3 ratio. That's what we have there. Okay, so what is the empirical formula for this product? So if we have, for every 2 iron, there's 3 Br2, okay, that is 6 Br. So that we have FeBr3. That is what we have here. But realistically speaking, because we had established a 2 to 3 ratio, the empirical formula has to reflect that. So we actually have Fe2Br6. This is what I would put for now, which is the empirical formula, because when we solved for the bromine, we would see that it had Br2, and if we got a 2 to 3 ratio, we have we have 6 Brs in total. So let me put C, empirical formula, okay, and then it's asking for the balanced chemical equation. Okay, for this, and because we have Fe2Br6, we can actually do, and I guess simplified form, we have Fe2Fe solid plus, and let me check here, what's it, liquid bromine, perfect. So liquid bromine, so that would be 3Br2 is going to turn into, now we can kind of put it this way, where it's 2FeBr3. So I'm kind of competing this one. I think it would be best just to put Fe, because it has it there. Yeah, I'll put Br6 here for now. That's what I'm thinking, but this would be the equation we're working with here. That is what we would have for the product. Now the name of this, okay, we have iron, okay, so right now it's asking for the name of product. So we have the iron, okay, and we have the bromine. So iron, bromine, but bromine, the oxidation number for bromine, because it's a halogen, it'll just be -1. And if there's FeBr3, if we have a -1 there's 2, then that's -3 in total. So iron needs to be +3 to make up for it. So now we know iron's charge is going to be +3. So based on that, the name of the product is going to be iron 3 bromine, but then you drop the INE and replace it with IDE, iron 3 bromide. That is the name of the product. And then F, which statement or statements best describe the experiment summarized by the graph? When 1 gram of iron is added to Br2, iron is a limiting reagent. Okay, we'll keep a note for that. When 3.50 grams of iron is added, there's an excess of Br2. You notice that even as the mass is increasing here, there's no more product, because now we've run out of bromine here. When it hits a plateau, like right here, it's because we've run out of product. Oh, sorry. There we go. We've run out of product. I mean, not product. We've run out of bromine gas. Here, in this whole increasing, not the plateau yet, iron is the limiting reagent. Okay? So, with that being said, if asking for best statement, so far 1 is correct. 2, we see that there's no more of the bromine gas, so that's incorrect. 2.50, both reactants are used up completely. So as you can see here, it's actually 2, this point right here, where both are used up completely. So 0.3 is also incorrect. And then number 4, when 2 grams of Fe is added to Br2, 10.8 grams of the product is formed. The percent yield must therefore be 20%. So let's see here. It looks like 11 to me. Maybe it is just 10.8, which would make a lot more sense if my math looked a little bit off. But nonetheless, though, we have 10.8 grams of product is formed. The percent yield must therefore be 20%. This would be, because 11 grams is formed, percent yield is based on the how much was actually formed versus the theoretical value. So 2 grams of iron, as we saw here, was this much moles. And using this formula here, okay, we see that it's a 1-to-1 ratio. So we would actually get the same 0.0358 moles of this. And then converting that over to a, I guess the molar mass, we have going to be, so iron 3 bromide, based on the periodic table, is going to be 55.845 plus 3 of bromine, so that's 79.904 times 3. Alright, so that's a big molar mass of 295.557. Okay, and now we multiply that by that number, the 0.03, to see how much we would actually get. Theoretically, we get 10.58. So somehow they got more product formed than even possible. So the percent yield would actually be not 20%, but this, because it would be 10.58 is a theoretical. So 10.8 minus, well, actually just divided, yeah, 10.8, and we have to find the, I guess, yeah, divided by the 10.58, our percent yield is 102%, okay, which is not correct either for number 4. So the only one that's the best statement here would still just be the first one. And with that, let's see how we did for this, okay. Yes, so 2 grams of the 11 gram product make 9 grams of Br2. So now we have 9 grams divided by 159.808, and we get 0.56. They rounded to 0.6 there and 0.4 here, but we still get 3 moles of Br2 and 2 moles of Fe. So the empirical formula, I still have Fe2Br6 just because I wanted to just translate directly, but that is correct, FeBr3. And we still get the same balanced equation, which is perfect. And the name is indeed iron 3 bromide, and only one is correct, okay? 11 grams of the product is formed when 2 grams of Fe is added. The percent yield is 100% and not 20%. So the reason why this one's a little bit sketchy, just because exactly as we calculated, our theoretical percent yield based on the amount of iron there was should have been like 10.5 something, but let's say based on the fact that it was 11 on the graph, we would actually still have 10.8 divided by 11 times 100 to get a percent yield, and that's 98.18. So it's nowhere near 20% yield. So this is still correct. And we can move on now to question number 7.